This is Mrs. Jackson. This is Chapter 3, Section 7, Part 1. And I'm losing my voice, so I'm going to do my best on this video. In this section, we're going to talk about the features of the graph, specifically the intercepts, the Y-intercept, as well as the X-intercepts, which we call zeros. And then we're going to get a little practice in finding those intercepts. Okay, let's get started. As in our experience with all of the functions we've looked at so far, knowing what the Y-intercept is and knowing what the X-intercepts are can help us go a long way in sketching out a graph of that function. In the case of polynomial functions, they can get pretty complex very fast, and some of them cannot be factored or broken down in any way, in which case we're going to rely on technology to help us graph. But in this section, we're really going to focus on those polynomial functions that can be broken down or where we can figure out what those intercepts are. Okay, so remember, it's important that the textbook calls the X-intercepts the zeros. So I'm going to use those terms, as one and the same. The X-intercepts are where the function crosses the x-axis, and that's also what we call the zeros. And the Y-intercept is where the function crosses the y-axis. All right, when it comes to identifying the Y-intercept of a function, it can be pretty simple. Remember, we've talked about this before, that every function has exactly one Y-intercept. You're never going to see more than one Y-intercept. If you do, it is not a function, as it would fail the vertical line test. If the polynomial is in standard form, and you know what that means, descending order of exponents. If it's in standard form, then the Y-intercept is the constant. And that's because the Y-intercept happens when x equals 0. So all along this y-axis, x is not positive, x is not negative, x is 0. So if we plug in a 0 for all the x terms, then whatever number is left, the constant, is going to be your Y-intercept. If the function happens to be in factored form, which we'll definitely encounter, then you're just going to go ahead and substitute x equals 0 into that function and then solve for your resulting y. So zooming in here on an example in standard form, we would always evaluate at x equals 0 to see what our resulting y-intercept will be. And you'll notice right away that the x terms, any term that has an x in it, is going to reduce to 0. And so the constant is going to be our y-intercept. And if we are already in factored form, you're going to do the same thing. You're going to evaluate the function at x equals 0. Anywhere you see an x, you're going to replace it with 0. And simplify the function using the correct order of operations. So in this case, we're going to have to do our exponent simplification first. So negative 2 cubed is going to be negative 8. And negative 8 times a 1 is negative 8. And negative 8 times a positive 3 is going to give us negative 24. So that would be our y-intercept for this function. And you can always evaluate the graph itself. Not always, I should say. If the y-intercept crosses right on the grid, then you can evaluate it. Otherwise, it's a bit difficult. You don't want to be approximating something. You want to have an exact y-intercept. So in this case, it does appear that we're crossing the y-axis right at y equals negative 3. So as long as you're an integer, you'll be able to evaluate from a graph. All right, let's talk about the x-intercepts, or the zeros of a function. As you already know, a polynomial may have actually 0, none, 0 x-intercepts, or many x-intercepts, depending on the function. And if they do exist, then we're going to find them at y equals 0 because, of course, all along the x-axis. Y is not positive, y is not negative, y is 0, all along that axis. So to find the x-intercepts, we're going to set the function equal to 0 and solve for x any which way we can. So at this point, we've learned a lot of different techniques, but definitely the recent polynomial identities are going to help us further break things down beyond factoring. Okay, at this point, we've already gotten some practice using all the various techniques that we know of to factor. So I've got 3 examples here that we're going to use. And of course, we're going to set this function equal to 0. So our output's going to be equal to 0. I'm going to switch it around and put the 0 on the right side. I just find it a little bit easier. By now, you may already start to anticipate one way to factor this, and that is we've got 4 terms, so try to factor by grouping. Out of the first 2 terms, we can take out an x squared, and what would be left then would be an x minus 1. And out of the next 2 terms, we could take out either a positive 4 or a negative 4. We're going to want to take out that negative 4 so that we have remaining in the parentheses exactly x minus 1. That's what we're hoping for. Keep your equation going. I notice a lot of people, when they start to factor, they start to drop this equation. We don't want to do that. So because x squared is multiplying x minus 1 and negative 4 is multiplying the same x minus 1, the distributive property allows us to bring these together. And we have 2 factors. Really, we actually have 3. As you know, we're looking for 3 solutions. Some of our solutions may be not real, and if they are not real, then they are not zeros. They may be complex solutions which have an impact on the graph, but they certainly will not result in intersection of the x-axis because that's a real number line. But in this case, this here is a difference of perfect squares. So you can further factor this. If you see it that this is factorable, you may do so. I found most of my students end up just setting this equal to 0 on its own. And if you're careful, you're going to end up with, sorry, I forgot my square here. Remember, you're going to end up with 2 solutions out of this. When we take the square root, we're going to end up getting the positive and the negative 2, both result in the perfect square of 4. So that's where we're going to get 2 solutions. And then on the third factor here, x minus 1 equals 0, we get x equals 1. So we have 3 real zeros here with this polynomial. So this function will cross at x equals negative 2, at x equals positive 1, and at x equals positive 2. And while we're at it, we probably should go ahead and note what the y-intercept is. The y-intercept is going to be that constant 4. So we know a lot of information about this graph. We know 4 different points really on the graph, which can help us sketch it pretty quickly. All right, next example. Notice in this example that there is no constant. What does that mean to us? That means that our y-intercept is 0. And whenever we have a y-intercept that's 0, that means we also have a 0 at 0, an x-intercept at 0, because we'll be going through the origin. So that's kind of something you can anticipate looking into this. All right, so we're going to set this function equal to 0, and we're going to try to factor it any which way we can. Notice that an x squared term can be taken out right away. So we can factor out an x squared term, And what we have left is x to the fourth minus 3x squared plus 2 left. Now this here is not a quadratic, but it is a 3-term quartic, if you will, and I think we've gotten some good experience so far in treating that like a quadratic. So by that I mean we can look at what a times c is. So our a here is 1, our c is 2. So we can make our little table. AC equals positive 2, and our b equals negative 3. We're looking for factors of positive 2 that sum to negative 3. There's only one way you can get positive AC and a negative b, and that's if both of the factors are negative. And pretty simple to see what those are. So now we're going to go ahead and start to factor by grouping. So I've got my x squared out here. I'm going to go ahead and put some brackets. So I'm going to replace my negative 3x squared with negative 2x squared minus 1x squared plus 2. Doesn't matter what order you put those in. And I am going to keep going here with this. I got my x squared out front, and I've got my first two terms. See what you can pull out of here. It looks like an x squared. Can be pulled out. What would be left is x squared minus 2. And out of the next two terms, either a positive one or a negative one is the only thing we could take out. And we're going to want a negative 1 so that we have x squared minus 2 left over. We'll want that same thing. And now we can bring our two terms here together. X squared minus 1 can come together because these are identical. So we've got our x squared out front, and we've got x squared minus 1, and we've got our x squared minus 2 left, equal to 0. And now we're going to put each of these factors equal to 0. They look like 3, but we really, believe it or not, we have one factor here, 2 here because that's a difference between perfect squares, and we have 2 here. They just happen to have the same value. All right, I'm going to move over here. So if I put x squared equal to 0, x squared equal to 0, take the square root of both sides, I get 0. Really, because this degree here of this very simple equation is 2, I kind of have 0 twice, if you will. We're going to talk about that in the last video of this chapter. I can factor x squared minus 1 if I want to, or I could just solve it here. As you know, that can factor to x plus 1 times x minus 1. But we'll end up getting the same result if we're careful. So when I take the square root of both sides here, I end up getting positive and negative 1. So I get 2 solutions there. Kind of get 2 zeros there. 2 real solutions here. And my last one, and I'm running out of room here, x squared minus 2 equals 0. X squared equals positive 2. And when I take the square root of both these, remember we're going to get 2 solutions. I get positive and negative square root of 2. It's irrational, but they're also real numbers. So we have quite a lot of information on this particular polynomial. We have a y-intercept that goes through the origin. That means that we also have x-intercept there at x equals 0. We have 2 real solutions here, 2 more real solutions, positive and negative 1. And 2 more real solutions at positive and negative square root of 2. So quite a lot of information we got from that polynomial by factoring. All right, last example. Looks like we can try factoring by groupings. So we're going to try to take our first 2 and then our last 2. Out of the first I've got an x squared that can be taken out, and what would be remaining is an x minus 5. And out of the next two, the only thing I could take out is a positive or a negative 1. They are both prime here, and so we're going to want to take out a negative 1 so that we have x minus 5 remaining. By the way, I had forgotten to set this equal to 0, so I'll do that now. Our x squared minus 1 can come together, and our x minus 5 can come together. Now we could put this equal to 0 and solve much like we did above, or you might want to get used to just spotting that difference of perfect squares and using our identity. So we've got 3 factors here. We're going to set them all equal to 0. So x plus 1 equals 0, x minus 1 equals 0, and x minus 5 equals 0. And we end up with, forgot my 0 there. We end up with 3 real solutions, in fact 3 integers. And we didn't talk about the y-intercept of this, but you can see very easily that the y-intercept of this function is going to equal 5. So we know a lot about all 3 of these examples just by breaking them down and picking apart these zeros, which we call the X-intercepts. Okay, I know this video was a little bit long, but I hope it helps. Thanks for listening.